This is problem 43 from chapter 13. A parachutist having a mass m opens his parachute from an at-rest position at a very high altitude. If the atmospheric drag resistance is kV squared, where A is a constant, not the spring constant, but just a constant, determine his velocity when he has fallen for time t. What is his velocity when he lands on the ground? This velocity is referred to as the terminal velocity, which is found by letting the time of fall go to infinity. So first we're going to find the velocity as a function of time, and then we're going to see what we get when we let time go to infinity. So in addition to the drag force, we also have the force of gravity acting on the parachutist, but those are the only two forces that we have. We are going to sum up the forces and set that equal to the mass times the acceleration. The velocity is going to be pointing downwards, and if there was no drag force, the parachutist would always be accelerating downward with an acceleration of g. But because there's this drag force, the acceleration is going to decrease. At terminal velocity, the velocity is no longer changing and the acceleration is 0. So as time goes to infinity, the acceleration is going to 0, and it's either 0 or it's pointing downwards. So I have kV squared pointing upwards. So when I sum up the forces, I'll say kV squared minus mg. That's equal to the mass times the acceleration, but I just want to use the magnitude of the acceleration. So since it's pointing downwards, I'm going to say minus ma, and then this acceleration is the magnitude, so this should be positive. So I already took care of the direction with this negative sign here. And the reason that I want to do that is because I'm going to replace the acceleration in this equation because I'm looking for the velocity as a function of time. So I have the velocity on the left-hand side of the equation. Rather than having the acceleration on the right-hand side of the equation, I want something else, which is going to include time. So acceleration is equal to the derivative of the velocity with respect to time. So if I plug that in here, from that I can get the velocity as a function of time after a little bit of integration. Okay, so then I'm going to divide both sides by kV squared minus mg, and I'm going to multiply both sides by dt. So then I have dt is equal to minus m dv divided by kV squared minus mg. Okay, so now see, the thing here was I had velocity on this side of the equation. If I'm going to integrate with respect to velocity, I need everything that has velocity in it on the same side of the equation. Okay, so now let's try and integrate and see what we get. The minus m can be outside the integral. I'm going from time is equal to 0. At time 0, the velocity is equal to 0 because the parachutist opened the parachute from an at-rest position. And then my upper limits of integration are just going to be v and t. When I integrate on the left-hand side, that's no big deal. I just get t. When I integrate on the right-hand side, things are going to be a little bit more complicated. However, I know from maybe the table of integrals in the back of the textbook. Let's check this out. Yes, so in Appendix A, I have the integral of dx over a squared minus x squared is equal to this. So this is what I want to use to do the integration. So I have to get my integral in this form in order to be able to do that, but let's just write this out first. So it's dx over a squared minus x squared, and that is equal to 1 over 2a times the natural log of a plus x over a minus x. And a squared is greater than x squared. Let's just write that down. Okay, so I'm integrating with respect to x here, and I have an x squared in the denominator. Here I have a kv squared. It's negative also. So let me pull out a negative k, and minus m, that's not going to fit. Let me just do this over to the side. If I have kv squared minus mg, and I want to pull out a negative k, then this becomes negative v squared. If I pull out a negative k from this, that would be a plus mg over k. So if I redistribute this negative k, it will get me back to what I have up here. So now I can pull the negative k outside of the integral, and it would be in the denominator. So outside I have m over k, and this is the integral of dv in the numerator. And then to get it looking just like what we have here, it would be mg over k minus v squared. So we're integrating with respect to v. We have our negative v squared here, so that means a is equal to mg over k. So we're going from 0 to v. Now I can go ahead and use this to say that that integral would be 1 over 2a. What is a? A is mg over k. So that's 1 over 2 times mg over k times the natural log of a, which is mg over k, plus x, which is v, divided by mg over k minus v, going from 0 to v. When we plug in the lower limit of integration, we get the natural log of mgk over mgk, which is the natural log of 1, which is 0. So for the lower limit of integration, we just get 0, so we don't worry about that. So I have t is equal to m over k, 1 over 2mg. Let's bring this k up to the numerator, and then this and this cancel, and this cancel, and I have the natural log of, I did something wrong. Okay, so this I said was equal to a. That's not true. This is an a squared. So a squared is equal to mg over k, which means this should be the square root here, and that should be the square root. And this would have been the square root also, so it doesn't cancel out. So this is the square root of k, and this is the square root of m. Okay, and then this is the natural log of mg over k plus v minus v. Okay, and we are looking for the velocity as a function of time. So we need to solve for the velocity, and let's first bring everything I have here over to the other side, and remember it didn't really cancel out. So, oh, but we could do this. If I have m divided by the square root of m, that would make this the square root of m, and then that would be gone, and that would be the square root of k, and then that would be gone. Okay, so now bringing what's left over to the other side, I have 2gt, and then the square root of k would be in the numerator, the square root of m would be in the denominator. This is equal to the natural log of the square root of mg over k plus v divided by the square root of mgk minus v. This is equal to e to, this was also a square underneath the square root. Okay, so e to the 2t square root of kg divided by m is equal to mg over k plus v square root of mg over k minus v. Okay, now we have to solve this for v, so we will bring the denominator over to the other side. So this is the square root of mg divided by k minus v times e to the 2t square root of kg over m, which is equal to the square root of mg over k plus v. Okay, and then rearranging a little bit, we have, bring this over to the other side, and we have mg over k e to the 2t square root of kg over m, bringing this over to the other side and pulling out the square root of mg over k. That would just be a -1. And then we still have this to take care of, which is going to go over to the other side along with the e to the 2t square root of kg over m. It was negative, so if I bring it over to the other side, now it's positive. You get to fill in the missing details on your own. Okay, and finally, not finally, almost finally, the square root of mg over k. To make it look a little nicer, we're going to say e to the 2t square root of kg over m plus 1. Whew. That is the velocity as a function of time, which is not the same as the answer that they give you in the back of the book, but it is correct. So you can check the answer in the back of the book. If you look at the units, they don't work out because the units that you have in the exponent here have to all cancel out, which is not the case for what they gave you in the back of the book, and I don't remember exactly what they did wrong. But this is what we should get here. As time goes to infinity, what do we get? As time goes to infinity, this gets really, really large, this gets really, really large, so the fact that you're subtracting 1 from something really large in the numerator and adding 1 to something really large in the denominator doesn't really matter, and the whole thing in parentheses here is just going to go to 1, so the terminal velocity is the square root of mg over k. And that concludes problem 43.